Okay, so this is Acids, Bases, and Salts, Lesson 4, and today we're going to talk about the Bronstedlowry theory of acids and bases. If you recall, yesterday we talked about the Arrhenius theory of acids and bases, in which we concluded that an Arrhenius acid is any substance that has H plus as the only positive ion in solution, and an Arrhenius base produces OH minus as the only negative ion in solution. Now we're going to look at another theory called Bronstedlowry, in which we're talking about hydrogen donors and acceptors. So in the alternate acid-base theory, which is also known as the Bronsted, B-R-O-N-S-T-E-D, Lowry, L-O-W-R-Y theory, there's two guys that discovered it. This theory explains the behavior of weak acids and bases. Where a Bronsted-Lowry acid are the proton donors. And last night we talked about proton being a hydrogen stripped of its electron. Bronsted-Lowry acids donate H plus to Bronsted-Lowry bases. So in this example right here, I have HCl and H2O, and then on the right you see I have H3O plus and Cl minus. So what happens is HCl donates its H to H2O, forming H3O plus, leaving Cl minus by itself. So this is considered the acid because it's donating H plus, and water in this case is considered a base, and you're going to learn something very unique about water in a minute because it's accepting H plus. So Bronsted-Lowry bases are the proton acceptors. Bronsted-Lowry bases accept H plus from Bronsted-Lowry acids. And it's in this example here, we have water plus ammonia forming an ammonium ion. So in this case, water donated an H to ammonia to form the ammonium ion, leaving OH, or the hydroxide ion, by itself. In this case, water is acting as the acid because it's donating H plus, and ammonia is acting as the base because it is accepting H plus. Let's talk about Bronsted-Lowry conjugate pairs. We're going to use two brackets connecting one side of the reaction to the other to represent the acid-base conjugate pair. Each member within the pair differs from the other by merely one hydrogen. So this is one of those things that it's easier to see, to understand. HCl is donating its H to water. So this is the acid, and when it donates its H, it's left as Cl minus. So this is considered an acid-base pair. This is the acid, and Cl minus is considered the conjugate base. They only differ by a hydrogen. Water is accepting H plus from the Bronsted-Lowry acid, therefore it's considered a base. And after it accepts the H, it forms H3O, which would be considered the conjugate acid. So this is an acid-base pair, also differing only by an H. Notice that the acid always has one more H than the base. Here the acid has an H, the base doesn't. Here the base has 2 H's, the acid has 3 H's. Let's do a couple of examples. We're going to use brackets and the key to label our acid base and our conjugate acid and our base. In this first example, water is giving up an H to NH3. So if this is donating H, this becomes my acid. This then is my base because it is accepting the H. This pairs with this because they only differ by a hydrogen, and this is considered my conjugate acid. And my acid and my OH minus are conjugates. If this is the acid, this is the conjugate base. In the next one, H is donating to water, making HCl the acid, making HOH the base because it's accepting it. Therefore, my acid-base pair are the difference between HCl and Cl minus, which makes this the conjugate base, and HOH and H3O, this is the conjugate acid because the acid always has one more H than the base. In the next example, HI is donating its H to H2O, so this is my acid. HOH is accepting the H, so this becomes my base. If this is my acid, then I minus is my conjugate base. And if HOH is my acid, then H3O is my conjugate acid. And in the last example, HNO3 is donating its H to H2O, so this becomes the acid. Water becomes the base. And if this is my acid, then NO3 minus is my conjugate base. And if this is my base, then H3O is my conjugate acid. What is the meaning of amphoteric or amphiprotic? Most of the time you'll see this one, amphoteric, but some textbooks still use amphiprotic. It's a substance that can act as either an acid or a base. So it can behave as a proton donor or a proton acceptor. In this case, H2O is donating an H to here, or the other way around. So this is acting as an acid, this is acting as a base. Therefore, H2O to H3O, this is my conjugate acid, and H2O to OH minus, this would be my conjugate base. Amphoteric substances must have at least one hydrogen in their formula. I want you to see in this example, in practice problem 1, water acted as an acid because it donated its H to NH3, and in practice problem 2, water acted as a base because it accepted H plus from HCl. Those are really good examples of amphoterism. So which one of the following substance is amphoteric? Well, we know it's definitely not this because it has to have at least an H. But Br has a -1 charge. So this can't accept. If this is -1 and H is +1, it can't accept anymore. SO3 has a -2 charge, and this can't accept anymore. This is +1, so I can't make this H3SO3 because this only has up to a -2 charge, so it can't be this. Here, SO3 minus is -2, and H is +1. So right now, the regular formula of this would be H2SO3, but because this is a minus charge here, it means it already lost an H, so this has the potential to either donate this last H, so I'll show you what that would look like. So we could do HSO3 minus plus H2O, and this could form H3O plus SO3 minus 2, or HSO3 minus plus H2O could also become OH minus plus H2SO3. So here it acted as an acid, and here it acted as a base. Okay, that's it for tonight. Tomorrow we're going to move on to pH.